Hello everybody, this is lecture 4 and maybe this can be considered as the continuation of previous lecture 3 because we are dealing with the minor loop gain and the load coupled converter. Okay, but in this lecture we are paying our attention on the relationship between minor loop gain and converter loop gain. Namely, the impact of impedance overlap at the output of upstream converter. So this impedance overlap is transformed as the impedance overlap. Okay, minor loop gain. Okay, we are using minor loop gain to characterize this one. So impact of the minor loop gain or on converter loop gain. Okay, so the minor loop gain obviously will change the loop gain characteristic of uncoupled converter. So what kind of change will occur? What is the relationship between minor loop gain and the converter loop gain? Or in another word, what is the loading effect? This is a loading, impedance overlap or minor loop gain is loading effect on loop gain. Okay, this is a very important topic and very interesting topic. Okay, so here you are reviewing the impedance overlap and the minor loop gain. Right? So again, I'm showing this. This is GL, is load impedance of this load subsystem, which is this one. This part is governed, controlled by this line filter stage, and this low frequency part is approached to this minus RIC. Okay, so this shows the negative resistance characteristic at low frequency. But overlap usually occurs here in the middle, okay? And this is the output impedance of this upstream converter. Maybe it looks like this and it goes like this, but we are paying our focus on this in this frequency range. And this is the plot of minor loop gain defined as the ratio of two impedances, all right? So GOU is small, and the GL is large, so this one becomes very small. Okay, same is true at this frequency range. So it starts out very small value, and it terminates at with very small value. In the middle, it passes 0 dB line, omega 1, omega 2, at which these two impedances meet each other. That's obvious, right? Because this one is the same, then ratio is 1 is 0 dB. Okay? And the polar flow trajectory of this one, we went through this, so this phase is bounded by this one, 180 degree to minus 180 degree. So it starts out here and it terminates like this. For extreme case, it will follow this line, but it never touches this because this is larger than this, so it goes like this and come back like this. Okay, so stable. All right, stability is okay. All right, so this is the polar flow trajectory, circular type polar flow trajectory, and somehow this is one example, and this is another example. Right, this is another example. So very similar to this, but little bit different. Okay, I intentionally make this case to explain something. Right, so this starts out from here, and it goes down the back, and it goes back to the origin. So this point is here. The system combined converter is stable, right? But to make this unstable, there are 3 ways of making this converter unstable. Okay? Fix the magnitude. Okay? Then just introduce the phase delay. Additional phase delay to this minor loop gain. Right? Then this whole thing will be rotating. This circle will be rotating. If this one is rotating by degree of this much, then it passes this critical point, then system becomes marginally stable. It starts generating sustained oscillation. That is called what? Phase margin. Okay? There is one phase margin, and there is another phase margin. If you introduce phase lead, phase advance, not phase delay. Okay, phase delay is rotating this whole thing in clockwise direction. Phase lead, phase advance is rotating this whole thing because magnitude is fixed. That shape remain the same. This thing only rotate. If it rotate by this much degree, then this part passes here, then system becomes marginally stable. Okay? There is a two-phase margin. One is this one is this one. Okay? For the conventional case, you are dealing with this system, and system is system is stable, and this is a unit circle critical point, and this is the phi. This angle is a phi. Then phase margin is a phi. Okay. If the phase delay of phi is introduced to the loop gain, while the magnitude of the loop gain remains the same, then this trajectory will rotate this much and it passes this critical point, and system start oscillating. Okay, that is the definition of phase margin in automatic control. Okay, here we have two phase margin. One is rotation of this direction due to the phase delay, and this another margin here. This is the phase advance. Okay, due to the phase advance this much. Okay, so Tm GL, okay, phase margin of 45 degree. If phase delay of 45 is introduced in here, then system becomes unstable. Okay, I don't know. Okay, you should think about this. Okay, so the impact of phase here and here is opposite. Okay, so one is, if you consider only phase delay, one phase margin belongs to here, another phase margin belongs to here. Okay? If you consider this thing as one thing, then you have two phase margins, one against the phase delay, the other one against phase advance. Okay? Okay, let me explain this. I intended to explain this first, but somehow I jumped into this graph. Okay, so this graph is so interesting. Okay, I derived this way of defining phase margin. Okay, this is my not invention, my thinking. Okay, so this is very useful, very useful. All right, later on, with this, we'll generate the specification for the load impedance. Okay, all right. So first, let me explain this. Okay, you are moving back to the basic. So this is the closed loop transfer function, and this is the open loop transfer function. So the relationship between closed loop transfer function and open loop transfer function is this one. So this is the single loop system, and the feedback is extracted at the output of transfer function. There is a special case. Okay, so in your control book, they are considering is all this special case. Okay, so in the electronics, people are using illegally this formula for all the feedback amplifiers. That's their fault. Okay, that is wrong. Okay, but consider this simple case. Then when Tm becomes -1, this is -1. This denominator becomes 0, and this becomes infinity. Okay, then system becomes unstable. You understand this, right? Then when this happens, Tm becomes -1, magnitude is 1, and the phase becomes -180 degree. This is the same as this one. Okay, if that occurs, then this closed loop transfer function becomes infinity. Okay, so it generates oscillation even without any input. 0 times this gain is generating some finite value. That value is appearing as the sustained oscillation. Okay, this is the principle of making the oscillator, right? Well, we are not interested in oscillator. We are interested in power supply. So this is unstable case. right? So if it passes this, then magnitude becomes 1, right? Radius is 1, and the phase becomes minus 180 degree, okay? So it rotates this much, then it passes this. At that frequency, this magnitude becomes 1, and the phase becomes minus 180 degree. Okay, this situation occurs, all right? So it becomes unstable, okay? Another case, consider this minus real axis. Phase of this minus real axis is minus 180 degree, okay? So phase is minus 180 degree. At that point, at that frequency, magnitude is this one. Distance between this point and this point. If this becomes 1, then with phase is being minus 180 degree, and the magnitude becomes 1, there's this point, right? At that case, this trajectory is passing this point at that frequency. That becomes what? System becomes unstable, okay? So in this diagram, there are 3 cases of being unstable. One is phase is fixed, okay? Phase is not changing at all, but magnitude is increased this much, then that becomes unstable, okay? Magnitude remains the same, so this circular shape, radius and the shape remain the same, but it's rotating, right? Then it becomes unstable, right? So phase margin at this frequency is this much, but this is the margin against the phase advance, not phase delay, okay? So PM1 is this one, angle in between, which is this. So margin in phase lead of the TMN. TMN is this one. Phase lead is lead of this one. Phase is phase lag of this one, because it comes in the denominator. Okay? All right. Another one here, phase margin at omega 2. This angle is margin in the phase delay of TM. Okay, this is a phase delay of this one. This is a phase advance of this one, because it comes in the denominator. Okay, and when we are talking about the phase margin and gain margin, the other one should be fixed. Okay, so this one is the 2 of these margins are defined with TMN fixed, right? And this one gain margin. If the gain, okay, maybe this one increase in this one or decrease in this one, they're the same. Effects are same, okay? Then if it is increased by this much, it passes here. So this is the same as the definition of gain margin in this conventional case, okay? Conventional case gain margin is defined for cases. Suppose something like this. Oh shit. This distance is related with the gain margin. Okay. So you have 3 margins. All right. So this is very important, very, very important. And this is, maybe you have seen this kind of thing for the first time. Okay. So this is an extension of the Nyquist story, okay? Because the loop gain of our case is different, very different from the conventional one, something similar to this. Okay, let me give you one example. Here. Oh, okay. Oh, this one is also example. All right. So we have, this is a margin, right? PM1 is margin against what? Against phase advance, right? So this is the magnitude curve, and this is the phase curve of the minor loop gain. So when you are considering the phase margin, this is fixed. This is fixed, and the phase margin PM1 is this distance. The reason for this is if you increase this one, you are putting some phase advance of this much. Then at this frequency, when this magnitude becomes 1, radius becomes 1, phase becomes minus 180 degree. This is the same 180 degree is the same angle as minus 180 ADD because it's circulating. Okay. So obviously this is phase 1. So this angle is same as this angle. And here, so this is phase 1, phase margin 2. If phase delay of this one, this much is added with this one fixed at this frequency, phase is becomes minus 180 degree. So obviously this is the phase 1 and phase margin 2, this phase margin 1, and this corresponds to this number, this distance, and this corresponds to this number, this distance. Okay, right? Okay, so now phase is fixed. This one is fixed. Okay, so then this is increasing. This is increasing, not decreasing. This is increasing this much. Then at this frequency, where this magnitude curve passes 0 dB line, phase becomes 180 degree, becomes unstable. Right? So this is the gain margin. Phase margin 1, phase margin 2. All right? If you reduce this gain, okay, then I don't know. Okay, forget about that. If you reduce further so it goes below this, then there is no problem. Okay, so these three numbers are important. So this defines the relative stability of minor loop gain. Okay, so this shape is entirely different from the converter loop gain. Okay, converter loop gain is very similar to the conventional loop gain, like this. The minor loop gain is different. So how we interpret relative stability of this system? Relative stability of converter loop gain will be different or not. We don't know yet. Okay, but which one we use? That is the big problem, big question. Okay, how about stability of this? Okay, that answer will be given in the next lecture. Okay, so as the final lecture slide of this part of lecture 4, this is I'm showing the example. You have seen this example a lot. Okay, so this is our typical case, and this is a polar plot trajectory of this minor loop gain. This minor loop gain. Okay, this is a minor loop gain. This is a magnitude curve. This is a phase curve, and this is a polar plot of this one. So it start out from origin and go around this. I'm not showing this, okay, because this is too large to show this. So I cut here, and it's coming back like this, okay. Then this is the phase margin 1. Phase margin 2. You cannot define this gain margin here. Gain margin will be very large, okay, because this is very small, okay. Crossover point is very near to the origin, so gain margin cannot be defined here. Right? And we translate these things into here. Then, same as the previous lecture slide, this angle difference is PM1, phase margin number 1, and this angle difference is, this distance is phase margin number 2. Okay, so this is gain margin of 22 dB. So maybe the crossover point is here, might be 0.1. Okay, so very close to tell the difference, right? So, but from this Bode plot, this is 22 dB. So if you increase gain, this is 10 times plus alpha. Okay, then it will go like. Okay, so this is very important, right? So this coming Thursday, we'll extend this story. Okay, and we'll find out the relationship between minor loop gain and conventional loop gain of load coupled converter. You will see a surprising result, very surprising result. Okay, all right, okay. We stop here. All right, thank you. Hi, everybody. This is the second class of lecture 14. In the previous class, we discussed the characteristic equation of load coupled converter, and we identified the minor loop gain as the critical element to determine the stability of this load coupled converter, and we discussed the relative stability and absolute stability of system of the load coupled converter using the minor loop gain. So this slide is kind of review of the previous lecture slide, but I'd like to provide you some fundamental information about the stability assessment of linear time invariant system. Okay, so this is the characteristic equation of our system. So it consists of two terms. One is 1 plus Tm nu parenthesis, and we have another one times this factor times this part 1 plus Tmn equals 0 is the characteristic equation of load coupled converter. So this is some somewhat strange situation, unusual situation. Usually for the system, 1 plus loop gain equals 0 is the characteristic equation. We start out that expression using the ET expression of loop gain of load coupled converter. That equation is modified in this manner. Okay, so we start out the standard format 1 plus Tml equals 0, and through some simple manipulation we identify this term. If this term is 1, then this is what? Characteristic equation of uncoupled converter. Okay, so because of the loading, you have additional term like this. Okay, okay. So forget about this part. Assume this is 1. So it's not here. Okay, this is 1. Then Tmn is the minor loop gain defined as GOU divided by GL. So there is no loop. It's not a loop gain compared to the regular loop gain. It's just the ratio of two impedances. But in this form equals 0 is characteristic, and this term equals 0 is also characteristic equation. So in terms of its function, in terms of its role in the analysis, it is performing the function of what? Loop gain. Okay, so we call it loop gain, minor loop gain. So loop gain is very general concept. We don't need any loop. Okay, suppose you have some equation 1 plus Tm equals 0. The origin of that equation can be the feedback system or something else. It really doesn't matter. Then still you can use Nyquist stability criterion to determine the stability of the system. Okay, so now assume this is not present, so this is 1. Then think about this. Okay, so Tmn, okay, is the complex number. It has magnitude and phase. All right. So assume this under some condition. I'll explain what is the some condition. Under some condition at this frequency. So this usually S is complex frequency. It has real part and the imaginary part. But if we have imaginary part, this means what? Sinusoidal waveforms. Okay. So if you have real part, that is the sinusoidal decaying like this or increasing like this. Okay. So this is one particular example. So under some condition, when you evaluate Tmn, which is complex number, but this becomes 1. Phase is minus 180 and the magnitude is 1. Then there is the number minus 1. Okay. Then this becomes 0. Right. Then this is what? This is a solution of characteristic equation. There is the pole of the system, eigenvalue of the system. Okay. That means in complex plane there is a real part and this is an imaginary part. This one is nothing. One is just it has some intermediate load. Okay. Final load is at this frequency. This characteristic equation becomes 0. Then there is the root of this equation. There is the pole of this system. So we have one pole here on the imaginary axis. So this is what? This is the real frequency part. Okay, real frequency means physical frequency. Frequency we are using. There is an imaginary frequency only defined in mathematical term. Okay, so we are thinking about the general complex number. So this can be plus minus, all right? But in real world, we only have plus frequency. So there is a pole, then there should be another pole. Because root of this characteristic equation, it appears as if this is the complex number, you should have complex conjugate pair. Okay? So there is a one loop here, then another loop should be here. Okay? So system has a pole at this frequency S plus minus J omega. Okay? In this case, what will happen? The system will oscillate without input, okay, at that frequency, okay. The frequency is exactly this frequency, omega 1, all right. So this is the general background of stability analysis of linear time imbalance system. Particularly, it determines the borderline of stability and instability, okay. Something is changing in this direction, and it hit this boundary borderline here, okay, then it goes this direction further, then it will show what? Growing oscillation, okay. If it move this direction, it will show what? Decaying oscillation. So there is the definition of borderline between stability and instability. That is the basic knowledge you should have now, okay. Because you are a graduate student and you take the courses, many courses about this, okay? Maybe you forgot about this, or they never teach this one, okay? They explain something and they made the problem without explaining the real meaning, implication of this, okay? So this is the thing you should know, okay? Then everything becomes very clear, right? So another one is loop gain. You have seen is this one. At low frequency, loop gain magnitude is very large, and high frequency it decays to 0. Phase start out minus 90 degree, and maybe at high frequency, phase becomes minus 270, something like that, okay? But there is just one shape of the loop gain. Any shape can be loop gain. The shape we are dealing with is this type of one. Okay? Okay. So go back to the origin. Okay? So expression for the loop gain of load coupled converter, I didn't repeat here. Okay? That was previous lecture slide, and it will appear again in next lecture slide. Okay? So you don't have to worry about that. Anyway, the characteristic equation is simplified in this manner, okay? And the TMN is this one, GOU divided by GL. So this is the typical shape of GOU divided by GL, and typical shape of the GL is this goes straight, and it becomes negative, okay? And this part is the input impedance of this one with the output showed it. If this is not present, then GL will be something like this. So we are taking this part here, and we are copying this part from input impedance of this one with the output opened. Okay, I call it the frequency masking effect of this intermediate line filter. Okay. And so phase here is minus 180 degree, but it reduced to this minus 90 degree. Okay, there is some zero. Okay, there is a pole, but there is RHP pole. Okay, so phase wise 0. So phase is becoming positive from minus 180. It becomes to minus from minus 180 to minus 90 degree over the pole, RHP pole. Okay, so RHP pole is doing something good for us. And it goes up, and this is the inductor. So phase is 90 degree, and this is the general shape of output impedance of uncoupled converter. Okay. Usually the crossover frequency of loop gain, crossover frequency of this uncoupled converter occurs here. Okay, the peak value of our impedance occurs at the crossover frequency of this converter. Okay, that is the general trend. All right. So this is a crossover frequency. At this point, value of this and the value of this are the same. Same is true at this frequency. So omega 1 is coming first and omega 2 is coming later. Okay. So you plot the ratio between this. Okay. So when this is large, GOU is larger than this, and the magnitude of ratio becomes larger than unity. So it has this bulging here, this type, triangular type, and at this low frequency, this becomes small and this becomes large. So you are dividing small one with the larger one, then it becomes very small. Same is true here. In terms of phase is GOU is this one, GOU minus GL is 180 degree phase around here, okay? And at this frequency, this phase is minus 90 is minus 180 degree. So this is the asymptotic characteristic here. So slope is 40 dB per decade. Minus 40 dB per decade. So phase is, this is the phase. This is exact simulation result of this one, this system. So phase around here is 180 degree and the phase around here is minus 180 degree. Okay. So everything makes sense. All right. So first this frequency occurs here. Okay. So they meet each other at this frequency. So omega 1 is this one and omega 2 is this one, because this is the crossing of a point, omega 1 and omega 2. Okay, this is the Bode plot, and convert these things into polar plot. Then at low frequency, this value, magnitude is very small, so it starts out from very small value here, origin, and the phase is 180 degree. Okay, but this is something else. Okay, so it is very similar to 180 degree. So it goes like this, and it come back like this, and it go like this, and at high frequencies, magnitude again becomes very small, and the phase is approaching this minus 180 degree. So it comes back in this fashion. Okay, so this is the polar plot. Okay. And the Nyquist criterion says this polar plot encircles this point. Encircle means you start out here, you go back to the origin without crossing this. It's not encircling. Okay? If you encircle something, then you should cut my hand. Okay? This is encircling. If this trajectory encircles once, there is one RHP pole. It encircles twice. There are two RHP poles. Okay, so that is the result of the Nyquist stability criterion. So that's simple. Okay, very simple result. So you are using that. Even though this shape of loop gain is something unusual, the principle holds. Okay, because the Nyquist criterion is mathematical derivation. So just cutting this hand is telling the presence of unstable pole. Okay, so this is stable. This stable. But if the phase and omega 1 frequency here, this is the 0 dB. 0 dB means the ratio is 1. That means magnitude of this one are the same. Okay, at this point, phase is this one, and it is smaller. Oh, it is okay. All right, it is small, or it is smaller than 180 degree this much. Okay, but there is a phase advance is introduced. Okay, assume the magnitude remain the same. This ratio, this transfer function, this minor loop gain, you only multiplied this by some no. You didn't change the magnitude of this, but somehow you add some pole and zeros, okay? There is a the phase advance. Phase advance means this trajectory is rotating without changing the shape and the length, okay? So it is rotate up to this degree, this much of a degree, then omega 1 is coming here, and at that frequency, magnitude of this polar plot, this TMN, is 1. Okay? This is the unit circle. Distance between this origin and this point is 1. And phase becomes what? Minus 180 degree. So it becomes this number. Then the story follows. I explain. Then it's the oscillation at this frequency. Omega 1 frequency. Omega 1 frequency. Okay? So we call it phase margin. Now this system is stable, but if phase advance is introduced this much, okay, then it starts oscillation. If you add further advance, you increase the advance in phase, then it encircles this and it's the growing oscillation, right? Okay, so at this frequency, the phase of at this frequency and the distance to this 180 degree is phase margin. Okay, the phase margin was 64 degree, and the same is true for this at this point. But this point, rotation should occur opposite direction. That means we are adding some phase delay. So this is rotating in clockwise direction. So we have a margin of this much. Okay. If phase delay is increased this much, that means this remains the same, and this phase is reduced by 73 degree. Then this part is crossing. It looks like this, right? So it passed this point at the frequency of omega 2, right? Because this remains the same. We are adjusting only phases. So you have two phase margins. One is phase margin for the phase advance. Another one is phase margin against the phase delay. And this is the phase margin number 1, PM1, created at lower frequency. And second phase margin is created at higher frequency. We have two phase margins. Very unusual, but nothing is strange. This is the strict adaptation of Nyquist stability criteria. Okay? Now, phase is fixed, so you are only increasing this. You are multiplying this TMN with some constant. Then this trajectory is expanding. Okay, so maybe this point is minus 0.10. The negative real axis crossing over frequency is minus 0.1. Then you increase 10 times, then it will pass like this. Becomes unstable. Okay, there is the gain margin here. Okay, so in this graph, this is too small. You cannot see this, but in this Bode plot, so this is the fairly large distance, and the gain margin is 22 dB. So if you increase the gain of whole thing, not this one, only maybe this one, this upstairs one is okay, all right? Then you can increase until 10 times without being unstable, without oscillation. But if we increase gain further, it starts generating sustained oscillation, and you increase further, then it generates growing oscillation. Okay, right? So this is it. It's all about the previous discussion. Okay, so this is the stability determination principle of this load coupled converter. Okay, we are assuming this part is okay because this uncoupled converter is designed by us, so it should be stable with a good phase margin. All right, you are only worrying about this part. This is a newly added part. Okay, but somehow it is entirely decoupled. This part is this part. Decoupled is a product of them, but the root of this equation is union of roots of this equation. plus this equation. That means decoupled. Okay, there is no, suppose it has some pole here, the location of the pole remain the same. It doesn't, this term does not affect this previous pole. It just add new poles, okay, which is very good, okay, which is very fortunate, okay. Consider if you add something, this will change, then very difficult to analyze, okay. All right, so this is it, okay, about the minor loop gain and the stability assessment of using minor loop gain, okay. And this story is even more dramatic, okay. Take a look at this. So this is the same situation, and this is the equation of the loop gain of load coupled converter, uncoupled converter, and the minor loop gain, which is the ratio of two impedances defined at this interface, okay. All right, so this is typical way. I'm using the same example over and over again. So this is GL and this is GOU, and this is what? First crossover frequency of minor loop gain, second crossover frequency of minor loop gain, and I marked omega C here. Omega C is loop gain crossing over frequency of this upstream converter with uncoupled condition, okay. So why it is here? I said the peak of this output impedance of uncoupled converter usually, probably always occurs at the loop gain crossover frequency of this converter. So omega C should be here, okay? So omega C crossover frequency of this loop gain, uncoupled converter loop gain should be located in between omega 1 and omega 2. Okay, this is the usual case. Okay, maybe you may have something like this, and you may have something like this. Okay, but this usually occurs in between. Okay, in the textbook, I consider the three cases when omega C is somewhere here, omega C is somewhere here. That case is very trivial. Okay, so this is the most common case. Maybe 99% is this one, and this is the most complicated case. Okay, so in my text, in my book, I analyze three different cases, but I don't need to explain everything here because there is the special example which is much simpler than this case. Okay, so I plot this is TMN defined like this. Okay, so this is different, right? So the increasing slope and decreasing slope becomes much faster here because you are impact of increasing impact here, decreasing impact becomes increasing impact, right? So this slope is much faster than this, and slope is much faster than this. Okay, so this omega 1, omega 2 in between, we have this omega C, right? So this is the general case. Maybe 99% of practical converters will be doing like this. Okay, and this one is the experimental result, and this is the theoretical one. So they are well supported by experiment. Okay, this is the part of dissertation of my student, Indian student. Okay, and also this is a part of our paper. Okay, so here, so this is the first and this second. What I'm trying to do is I'd like to show to get the asymptotic plot of this from this structure. This is a construction structure. So this is the first picture, second picture, and the second picture is repeated here. Okay, second picture is repeated here, and this is the first, same thing, and first picture here. Okay, so we have omega C here, and we have omega C here. So this is the TMN. This is a TMN. This is a TMU. Okay, I can immediately construct the asymptotic plot, frequency plot, Bode plot of TML from this graph. Okay, let me show this. Okay, I start out here and I put this and take the symmetrical mirror image with respect to this real axis. So I draw here and like this, okay? So it goes like this, goes like this, right? So this is flipped over this real axis line. So it starts from here and here goes like this. And after this omega c frequency, it follows this one, TMU, but there is some peaking here. So I'll explain why this peaking occurs, and the magnitude of peaking can be calculated, and that you connect, start at low frequency. It follows the mirror image of this minor loop gain. At high frequencies, after this frequency, it follows the TMU. We verify this. Okay? So result is on your printout. This is a simulation result. Okay? Simulation result. So this part is TML. So this is the mirror image of this. Okay? And after this, it follows, this is the TMU, okay? But it should go from here to there. In between, there is also equation. I'll show that later. But in simulation, it looks like this, okay? So, it is, maybe it looks very difficult to sketch this from this one, but that is easy, okay? So, this is a TMN. Then flip this over against this real axis, and you have this. And after this frequency, omega 2 frequency, track copy the TMU, okay? And in between, there is a peaking, so smoothly connect them. Then you will get this, okay? So this is the final result. And intermediate step will be explained later. And I magnified this part. I magnified this part. I zoomed in this part shown here. Okay. So relationship between this and this, the symmetrical mirror image with respect to this is the relationship is this one. 1 over TMN is TML. TML becomes 1 over TMN. If you have this expression, then you know this, then you flip over, then you will get this. Okay, think about this. This is obvious. Okay, this is very large, that this becomes small, and this is very small. This becomes large. Okay, opposite. Okay, in terms of phase, this is 180 degree minus 180 degree. The phase margin remain the same. Okay, let me explain that later. So before this frequency, this is omega c frequency, 0 dB crossover frequency of loop gain of uncoupled converter. So this is the omega c, this point, okay? And this second point is, actually this is the omega 2, okay? The second crossover frequency of this minor loop gain is here, okay? After this frequency, it follows TML, follows TMU. TMU is not shown, but TMU is somewhere there. So this is a TML, and the TMU becomes the same. And in between, you should go from here to there. You don't want to go like this, okay? Go smoothly, okay? Then this one is the result, okay? And in terms of the polar plot, so up to this point, up to omega c, this is the part of TML. TML is this one, and this is the TMN, okay? Or this one is the TMN, and this one TMU. So they have same equation, okay? One occurs here, and the other one occurs there, okay? So TMN is GOU divided by GL, and the TML is GL divided by GOU, okay? I'll show the one example, how to find out the relationship of this inverse relationship, okay? You flip the magnitude plot against the real axis, and get the mirror image, and you rotate to phase by 180 degree, then you will get this. Okay. The consequence of this is crossover frequency, the same. Okay. Crossover frequency of TMN, TML is the same. Okay. And the phase margin of TMN is this angle. Phase margin of TML is this one. TML is obviously defined against the phase delay. This one is defined against the phase advance, but they are the same. Okay, they are the same. This is the final result, and justification is coming later. Okay, this is true. Okay, and this relationship TML is 1 over TM. So TML is GL divided by GOU, and the TMN is GOU divided by GL until 0 dB crossover frequency of this uncoupled converse loop gain. Okay? Understand this? So the stability is the same. Okay? Because it has stability margin. Here it has stability margin. So stability same. Phase margin is the same. Gain margin the same. And this omega 1 is the what? This is the crossover frequency of loop gain of load coupled converter is the same with the minor loop gain. Okay, so everything is the same. So the minor loop gain and converter loop gain with load subsystem coupled are the same in every sense. High frequency can be different. Okay, but everything is determined here. Stability is determined here, and the phase margin, gain margin will be determined somewhere here. So they are the same. Okay. So the implication of this is you can program the phase margin, gain margin, crossover frequency, everything about the load coupled converter by what? Adjusting minor loop gain. Okay. So minor loop gain is determined by the filter design, line filter design. So by adjusting the parameter of this, we can program the loop gain characteristic of this, because this determines the loop gain characteristic of every characteristic of minor loop gain, and converter has all the same matrix as the minor loop gain. So designing, shaping the minor loop gain is the same as determining this converter loop gain with load subsystem connected. Okay. So this is very good result. Okay. So in this way, you can program the upstream converter by designing the downstream line converter. Okay. So this is called impedance conditioning. This concept is called impedance conditioning. Right. And I explained here why this omega C is in the middle of omega 1, omega 2. Okay? Because omega C is the point GOU. Get the highest value here. Okay? And this GL is going like this. Okay? So usually this is maybe not in the center, but somewhere here. Okay? This is a conventional design, practical design. If it comes here, then problem becomes much simpler than this. Okay? That is covered in the text, in the book. Okay? I think I distributed the copy of chapters. Okay? So in that is, so I wrote down here. Okay? Many people challenged this one. So to convince that poor people, I have written down here. Okay, I have written this in my text. Okay, this one, right? So construction, asymptotic construction of the loop gain, asymptotic loop gain construction. So this is our equation. This is our equation. There are three terms involved with this. One is TMU, TMN, and the multiplication of this. This is the addition of this one and this one, actually, in log scale. And this one is what? This is the 0 dB line. Okay, this is very trivial. So this three term is considered here. First, this is the TMN, okay, TMU, right? And next one is this one, TMU times TMN. How to construct this? You add line by line. So at this frequency, TMN is 0. So it becomes the same. This is 1, 0 is 1 here. Then this point is on this TMU line, and this one is on the TMU line, okay? And this point, this is 0, then this is a TMN line. So 3 point is automatically determined, okay? Then you add them together. For example, the length of this should be the same as this part. Looks different, okay? So I needed to change this figure, but I decided not to do because I can explain it, okay? So this different one is more educational, okay? Should be the same because you are adding this much to there, so it should go up this much, okay? Then this is the plug, okay? So we have this one, okay? We have this one, and the 0 dB line, okay? So of this frequency, we are thinking about this, okay? This remains the same, okay? TMU is the TMN, so we are adding this one, okay? So we are comparing this line, comparing 0 dB line, and with TMN is this one, okay? And TMU, we are comparing TMN is this one, and this is the TMU times TMN is this one. So you are comparing 1, 2, and 3. Each one is dominant. 3 is dominant, right? 3 is dominant. So we get rid of this. We ignore this. Then remaining is this. Then this one cancels with this. And the remain is what? 1 over TMN. Okay? So from the graphical construction, so up this point, so this is simplified. TML is approximately same as 1 divided by TMN. That means if this is the TMN, TML is mirror image of this up to this point. Okay? And in the middle, I'll show this. And after this frequency, after omega 2 TML is this one. So after this frequency, it follows this TMN. So should be this, okay? And in between, you want to connect this one, but there is a peaking. Okay, it occurs always. Okay, so there is a peaking. I'll explain the origin of this peaking. So there is a peaking. Then probably you want sketch like this. So this is the result of the asymptotic construction of this loop gain with load impedance connected. Okay, so of this frequency range, expression is this. After this, TML is very similar to TMU, and in between TML is TMU divided by TMN. Okay, so this is the simple verification. All right, so I divide into 3 frequency ranges. For this frequency range, this is true. TMU times TMN is much larger than this. Okay, then comparing this and this, you drop this. At this and also in this frequency, TMU times TMN is larger than TMN, obviously. Then you drop this. You first drop 1. Second, you drop TMN. Then remaining this, and you cancel this. You have 1 over TM. You know. Okay? And in this frequency range, so you have this TMN is much, much larger than unity. Then you skip, you kill this. Okay? And in this frequency range, TMN is larger than this one. This one is decaying fast because of something, because of this part is decaying fast. Then you ignore this. Okay? So you ignore this, then this is a TMU divided by TMN. Okay, you can subtract this to construct this. But in this short range, okay, just to hold on, right? And after this, everything becomes small, okay? TMN is smaller than unity, is below 0 dB, and this one is also below 0 dB. So you ignore this, and remaining is what? TMU, okay? So this is the construction of loop gain, okay? So at this frequency, according to this, it should land at this point, but there is some peaking, this here, okay? We go over this in the next slide, okay? So at this frequency, this relation is valid, okay? This is very good, extremely good. Okay, and the phase margin is determined at this point. Gain margin is determined somewhere, and crossover frequency is determined at this point. And there is a peak. So according to this relationship, maybe this one is, we need some detailed construction, but this should go like this. At this point, it should land at this point, but there is a peak, okay? Then magnitude of peak is determined by this 20 log 1 divided by square root 2 divided by 2 times cosine phase margin number 2. You have two phase margin. First phase margin was defined at this point, and second margin is defined at this point. So this peaking is determined by phase margin of this point. Okay, so I'll explain this later. Okay. Okay. This is the final result. This is my rule of constructing this, and this is the simulation result. Okay. If you take a look at the simulation result of this point, omega c frequency is loop gain crossover frequency of uncoupled upstream converter. So this part is just flipped over version of this one. Okay, and after this at omega 2 we have some peaking, and after that if it follows TMU. This is the TMU. This black line. Okay, and from here to there, using this you can construct this, but that is not necessary, that is unnecessary. So you connect them, and this is the real simulation result. And there are two curves. This thin line is experimental verification. So we verified everything here. Okay. So this one is simulation. This is the equation, and this is the empirical method. Okay. So this is true. People, they don't believe this. I wrote paper, and they didn't understand this. They didn't understand the value of these things. Okay, is maybe beyond their intellectual scope, probably, right? I cannot explain everything in short, in concise paper. Okay, so I was relying much on my readers, but they are not that brilliant. Okay, so I zoomed out this part. Okay, so this is the enlarged part of this. So TML and the TMN. Okay, and one is small signal prediction. This one is computational method. Okay, so probably I used the time domain simulation method, and somewhere else I used the experimental data. Okay, but they are the same. Okay, basically they are the same, and this is the difference between this one. This one was phase margin 1 defined against the TMN, and this is the phase margin defined by TML. So the same phase margin. Okay, phase margin is the same. Loop gain, crossover frequency is the same. Everything is the same, and this is determined by line filter design. So by designing line filter properly, you can program the performance of upstream converter. Okay, that is my claim, my basic claim. Right. So from DC to mid frequencies, precisely at the loop gain crossover frequency of upstream uncoupled converter. So loop gain of load coupled converter is given by the reciprocal of the minor loop gain. This relationship is valid. This one is valid at this low frequency. High frequency is something else, but we are not interested in. We are not really interested in this. Okay, but still you can predict this, right? So omega C is 0 dB crossover frequency of TMU, which is loop gain of uncoupled upstream converter. So the conclusion is the stability, phase margin, bandwidth, crossover frequency of load coupled converter are all the same as those of minor loop gain. So insinuation of this is there is a potential of performance programming. Okay, I wrote one paper about this performance programming. Okay. This is the to verify this relationship of this. I showed this in my book. So illumination of relationship between TML and TMN. So this is my example. So TMN is this function, and the TML was reverse of this. Okay. So one is this one is this one. So this is the symmetrical, perfectly symmetrical against the real axis. And the phase margin, they are the same. This distance is the same, and this is a polar plot of this. So it goes like this, and this one goes like this, but this angle remains the same. Okay, and direction is this direction and this direction. That is obvious. Okay, so TML magnitude is decreasing, and the TMN magnitude is increasing. Okay, so it goes out from origin and it moves to the origin. Okay. Understand this, right? Okay. Understand it and believe this. Okay, believing is important. Right? This is true. You cannot make any counter example of this.